All right, guys, we're going to start chapter 4 today. Chapter 4 is one of my favorite chapters. It's one of my favorite chapters. It's on thermochemistry. Before we start, though, I wanted to break this word up, thermochemistry, into thermo and chemistry. What does thermo mean?
Heat.
Heat. Thank you. So we're really going to talk about the chemistry of heat, which is really cool because even if you don't choose to go into chemistry later on in your life, you are going to be surrounded by these types of situations and you'll be able to describe them intelligently. After we go through this chapter, I promise you're going to understand heat a lot better. At least I hope so. So I've got a couple of pictures of some reactions that remind me of thermochemistry. This reaction right here is called a thermite reaction, and we're going to do it as a lab. We have to do it outside. It releases a ton of heat. In fact, it releases so much heat, it can melt metal, and we'll do that, and you'll see that. It's really cool. But also some common reactions, okay? A campfire or just a wood burning here. It's releasing heat. This is a chemical reaction. And what we're interested in this chapter, it's not good enough for chemists just to say, well, it gets hot. This gets really hot. But that's not good enough. We're going to quantify how much heat is released or absorbed in chemical reactions. And that's what thermochemistry is. Very interesting. I hope that you guys will follow along in your guided notes. So please have your chapter 4 guided notes open and follow along. I promise you're going to learn something. Ready? Okay, so what is thermochemistry? Well, thermo means heat. So it's the chemistry of heat transfers, right? Thermochemistry, here's the definition that I would like you to write down in your guided notes. Thermochemistry is the study of heat given off or absorbed during chemical reactions. Most chemical reactions will give off heat. Most of them release heat. But there are some chemical reactions that absorb heat. One lab that we're going to do in this chapter is you're going to make some hand warmers and you're going to make a reaction that gets cold, so a cold pack. And we'll see both of those scenarios, where heat is given off and where heat is absorbed. But that's what thermochemistry is. It's the study of heat in chemical reactions, whether it's absorbed or released. Okay, real quickly, I've got a couple of pictures on this slide that I would like to explain. This is a hot object, and this object is cold. This one's at a higher temperature. This one's at a lower temperature. Well, heat always flows in one direction. Which direction does it go? From the hot object toward the cold object. It will always flow that direction. Well, heat flows in one of three ways. Conduction. Let's talk about that first. Conduction is where you actually physically touch another object and there's a transfer of heat between one object and another one. Like this picture shows here, conduction. If you were to touch a hot pan, that heat is going to be transferred from the pan to your hand. You're touching it. That's conduction. Well, there's other ways heat can be transferred as well. Convection. Convection is actually the heat transferred in fluids. So like if there was water in this pan on the stove here, obviously it's getting hot from the bottom because that's where the heat source is. Well, that hot water will rise and it's cooler on top. Well, what that causes is little, what are called convection currents. The rising and the falling and the rising and falling. Temperature differences are causing that. So it's called a convection current. So heat is transferred through convection. But another example is radiation. So you can see radiation here is transferred of heat from a distance, so through space. A good example of this is the sun. The sun's heat energy is getting to the earth by radiation. It's traveling through space. So there's three ways: conduction, convection, and radiation. Which one do you actually have to physically touch?
Conduction.
Conduction. Which one is where it goes through space?
Radiation.
Radiation. And convection is where what happens? It's going through fluids, right? It's going through fluids. You'll see convection also in the mantle of the earth. So the inside of the earth, the magma there, it's going through convection currents as well. And sometimes that can cause movements in tectonic plates, and that's how earthquakes are formed. So. All right. Okay, let's go to what energy is. Energy, you hear it all the time, but it's actually a word that's really hard to define. What is energy? And this is the best definition that I think we'll start with here. Energy is the ability to do work or produce heat. So energy is the ability to do work or produce heat. Now in chemistry, most of the time we're going to be talking about heat. And you mostly talk about energy in terms of work when you're learning physics. But it does relate to chemistry as well. We'll talk about how work relates to chemistry as well in this chapter. But energy is the ability to do work or produce heat. So the SI base unit for energy is called a joule. So if we're going to quantify energy, we're going to measure it in terms of joules. How many joules of energy does it have? Joule is abbreviated with a capital J. Okay, and then it says here that thermal energy, which is heat, is an outward manifestation of the movement at the atomic level. Think about that for a second. So heat is the outward manifestation of the movement at the atomic level. What does that mean? Let me use this picture to explain it. This is an iron rod here, and they're obviously heating it up. If I'm going to call this point A on this iron rod, and I'm going to call this point B. It's made of iron, so point A or point B, which point are the iron atoms moving faster?
A.
A. How do you know that?
Because it's hot.
How do you know it's hot? You can see the color. It's red hot right here, right?
They're jumping.
The iron atoms here are moving very fast. They're probably still moving fast at B, but not nearly as fast as A, right? So that's what it means. Heat is the outward manifestation of the movement at the atomic level. And we talked about this in the gas law chapter. Temperature. Isn't the temperature in this room a reflection of how fast the air molecules are moving in this room? It is, right? We talked about that in the gas law chapter. So when the temperature goes up, say it was 100 degrees in here, the air molecules are going to do what? Compared to what they're doing in the room right now. They would have to speed up. They'd have to move faster, right? Okay. So that's what it means. All right, let's move on. Heat is energy transferred between objects because of temperature difference. That's very important. Heat is the energy transferred between objects because of their temperature difference. If this object right here, it says it's hot, let's quantify it. Let's say it was at 100 degrees Fahrenheit. And this one was at 50 degrees Fahrenheit. Heat is the transfer of energy. It's the transfer of heat energy from the hot object to the cold object. Will heat ever go from cold to hot? No, it always goes from hot to cold. So heat is always transferred from hot to cold. So let's think about that for a second, because I think that's kind of counterintuitive. A lot of you probably think it was the other way around. when you are outside, you touch a cold doorknob or something. Why does it feel cold?
Because you're losing heat.
Is it because the doorknob's cold is coming into your hand?
Absorbing heat.
Or is it like Tate said, is it because you're losing heat?
My name's in the video.
It's because you're losing heat, right, guys? So when you feel something cold, it's cold not because it's cold, but because it's at a lower temperature and your heat is leaving your hand quickly. That's what feels cold.
How do we know that? How do you know that it's heat that was?
Because you can track it. You can track the temperature of your hand and the temperature of the doorknob. Couldn't you quantify that? Couldn't you say that the temperature of your hand before touching it was at a higher temperature than after? Could you measure that?
Yes.
Could you measure the temperature of the doorknob? Yeah.
Yes.
You can quantify. You can do experiments on it. And you can prove it. There's a lot of evidence that it only goes from hot to cold. It never goes in the opposite direction.
It's like taking a bath. You know, the tub's hot and then
Yeah. Exactly. So why in the wintertime do you wear layers? What's your body temperature at? 98.6?
Yes.
What's the air temperature? Even in this room, what is it?
Colder than that.
70? If we're lucky today. So which way is heat moving? From your body to the air, right? So why do you wear a lot of layers in wintertime? To make it harder for the heat to leave your body. You're trying to trap that heat next to you. So you have a lot of layers. Right, Sam? Yep. Okay. Practice problem number 1. I want to see if you understand this. Let's talk about a different situation here. It says on practice problem number 1, explain how ice helps lower the temperature of your soda. Draw a picture and show the flow of heat. So let's draw a picture. Draw a big cup here. Okay, it's filled up with your favorite soda, and you put ice in it. Okay, I'm going to draw a giant ice cube, but there's a lot of ice. I want you to take a second, and I want to see arrows. I want to see temperatures. I don't know what the temperature of the soda is, but give it a temperature. Give the ice a temperature. Give the soda a temperature. And then I want to see an arrow. Which way is heat being transferred here? And try to explain how ice helps keep your soda cool. So if you're watching the video, please hit pause and try that. And then hit play once you have an answer. Okay, guys, let's see how you did here. A soda, when you get it out of the fountain place, wherever you get your soda, sometimes it's chilled, sometimes it's refrigerated, but sometimes it's not. What would you say a good temperature for the beginning of the soda would be? Should we say like 50? Maybe they put it in the refrigerator a little bit, it's chilled a little bit. So it's 50 degrees Fahrenheit. What is the temperature of the ice cube? Well, water freezes at 32 degrees Fahrenheit. Okay, now once we have numbers to it, we can easily see which way heat is going to be transferred, right? Does heat go from hot to cold or from cold to hot? Hot to cold. So I hope that you drew the arrow. This is heat flow going into the ice cube. So if heat is leaving the soda and going to the ice cube, what does that do to the temperature of your soda? Well, instead of 50, now it might go down to, I don't know, 45 degrees Fahrenheit. Or maybe even lower than that. Okay, if you've got a bunch of ice. But will this happen forever?
No.
How come?
The ice will melt eventually.
Yeah, when heat is being transferred into the ice, that's going to melt it. And so over time, the ice is going to melt. And then let's say you left this soda out for a day. You left it out on your counter for a whole day. You come back. What temperature is your soda going to be at?
It's going to be warm again.
If the temperature of the room was 72 degrees Fahrenheit,
So what is your soda?
what's the temperature of your soda going to be?
72.
72. How come?
Because it takes It's the heat.
Because it will eventually, the heat will be going into your soda until they are at an equilibrium with each other, right? They're at the same temperature. Does that make sense?
Yes.
So let me ask you this. Is everything in this room at the same temperature?
No,
It's not?
I don't believe so.
Everything but us. Aiden, good job. Is Aiden right, though? Is everything in this room at the same temperature but us? Think about that. Think about that. We're going to talk about it later on.
Some things absorb
Okay.
better than others.
Temperature and heat are very different. Okay, I hope that you will be able to explain the difference between temperature and heat after this slide. So write down the definition here for temperature in your notes. Temperature is a measure of molecular motion. Remember kinetic energy? Kinetic means moving. The faster the motion, the higher the temperature. So temperature is really just a way of quantifying how fast the molecules are moving. Obviously, if it's hot, they're moving very fast, the molecules. If it's cold, they're moving slower. So temperature is just a way to quantify how fast the molecules are moving in that particular substance. Let's contrast that to heat now. Okay, how is temperature different than heat? Here it is. Heat is the transfer of that kinetic energy. So heat is the transfer of that kinetic energy from a warm object to a cooler one. So when we look at an object, we can't really say and talk about it in terms of heat. It's got potential heat transferability, but when you look at an object specifically, we're going to say its temperature is high or it's low. But if it's in contact with something else, then we can talk about heat, because heat is that flow or the transfer of that kinetic energy from the hot object to the cold one. So do we see the difference between temperature and heat? Temperature is a measure of how fast the molecules are moving in that specific object. Heat is the transfer of that kinetic energy from one object to another. Okay. There's a lot of misconceptions out there about heat and temperature. And what I've got here is a YouTube video. This YouTube video is produced by a YouTube channel. It's called Veritasium. He's from, the guy that does Veritasium is from Australia. And so you're going to notice they say things a little bit different in Australia than we do here. Aluminum. How do you say aluminum when you're in Australia? Aluminium. Yeah. So when you hear that, that's what aluminum is he's talking about. But he's going to go through and he's going to ask people about heat and temperature. What he does, he puts out a lot of science videos, but he focuses on the misconceptions that people have about science. And then he teaches the correct science from the misconception, which is a really good idea. But if you want to watch his videos, it's Veritasium. They're really interesting. Here's just one of them. So let's watch it. I might pause it every once in a while to kind of talk about what he's doing.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. That's warmer. Yeah, way warmer.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it.
Okay, so let me stop it there for a second. That metal hard drive is obviously made of metal. The book, paper. All the people are saying, which one's at a higher temperature? The book. and the hard drive is metal and it feels colder, right? Well, let's do that experiment right here. You have a desk that's made of plastic material. Put your hand on the plastic material on the top. And now, with your other hand, touch the metal. Which one's at a higher temperature? Which one's at a higher temperature?
The one feels warmer.
Which one feels warmer? The desk, the plastic feels warmer, right? The metal feels cooler, doesn't it? So that's what he's doing here. Okay? Let's actually watch the video now and see what the misconception was. See if you guys can figure it out.
I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's cool.
Would you bet me money?
I do because I don't have any cash.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. And measure the temperature of that.
19.0. Alright, well now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature. They don't feel the same temperature though.
So why does that feel colder if they're basically the same temperature?
Good one. You got an answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Nice and cold.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
Much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates.
Okay, so I've actually got the same thing that he has right there. I've got an aluminum block and a plastic block. I'm just going to pass them around for a second and give you a chance to feel what they're like.
When you touch an object and it feels warm or cold,
I'm not a scientist. Come on, you tell me.
well I'll
Scientist, come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Nice and cold.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
Much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
I think so. Doing the colder.
Yeah, because it's colder.
Let's
And I
actually...
think they're going to go the same.
Alright, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
My God, it's melting.
This is melting quicker than that one, even though this is aluminium and that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea,
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature. Because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor, so heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay. I believe you.
Makes sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder, even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder and the book feel warmer.
Yes.
So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
Okay, guys, so I've got the same items that he had, an aluminum block and a plastic block, and you felt them, and the aluminum felt colder, right? So you would probably hypothesize that because it feels colder, it would not melt the ice as fast, right? Because it's colder. But let's actually see that. I want you guys to come up here and let's look at it. Okay, so I hope that you remember from now on, when something feels cold, it's because you're losing heat to it. And that's why it feels cold. Anyway, let's continue on with the notes. Let's go to the law of conservation of energy. What does it mean to conserve something, guys? Like when it says law of conservation of energy, what's conservation mean? It means to save. Okay? So, what does that mean? Law of conservation of energy. You're supposed to write it down. Okay, the law of conservation of energy states that energy cannot be created nor destroyed, but it can be converted from one form to another. So you can't create energy and you can't destroy it, but it can change forms. It can be converted from one form to another. So if you can't create or destroy energy, what does that mean? Well, here's what it means. The energy in the universe, in the whole universe, is it constant? Yeah, the energy in the universe is constant because we can't create or destroy it. Now it can change forms, and it does, but the energy is constant, right, Jessica? Energy can be classified as one of two things, either potential or kinetic. And you're supposed to write down the difference. Potential energy is stored energy. It's not being used at that moment. It's got the potential to do work or produce heat, but at that moment it's not. It's just being stored. Like a bottle of chemicals. It's not doing anything at the moment, but does it have potential to produce heat or do work? Of course it does. Well, the other form of energy is kinetic energy, and kinetic means moving. So if an object is moving, it's got kinetic energy. And in chemistry, we see a lot, we can use chemicals which have potential energy, do a chemical reaction, and it will cause something to move. We're transferring that energy into kinetic energy. But is the total energy constant? If you look at the whole thing, did we create energy or destroy it? No, it was always there. We're just converting it from one form to another. Okay, when we describe energy changes, it can be kind of confusing to students. It's a little bit complicated. So there is a well-defined way of defining which way the energy is going and being able to describe the energy differences. So please watch up here as we go through this. So when we describe energy changes, there's two things you need to be aware of. There is a system and there is the surroundings. The system, what that is the actual chemical reaction. That is the chemical reaction. Everything else besides that chemical reaction is considered the surroundings. And like you can see up here, a chemical reaction can either absorb energy or it releases energy. Most of the time, chemical reactions will release energy, but there are some chemical reactions that actually will absorb energy. Okay, now this is where I would pay attention. The sign convention can get a little confusing for students, and here's why. The sign convention for energy. If energy is absorbed, the sign is positive. So we see energy coming into the system. We're going to say that the sign of energy there is positive because it's gaining energy. It's absorbing heat energy. Okay, well just the opposite is true. If energy is released from a chemical reaction, we say that the sign is negative because the system, the chemical reaction, is releasing that energy, so it's losing it. So we say the sign of that is negative. Well, students get confused all the time because do we take the system's point of view or do we take the surroundings' point of view? We're always going to take the system's point of view. Okay? So we're looking at energy changes from the system's point of view, the chemical reaction. So if it gains energy, energy is absorbed, it's positive. If the chemical reaction loses energy and releases it, the sign is going to be negative. Okay, practice problem number 2. Let's see if you guys got this. Will the energy sign be positive or negative for a chemical reaction that absorbs energy?
Positive.
I hear a lot of positive. That's right. It is going to be positive. And also, will the surrounding temperature go up or down?
Down.
Okay, that one's a little bit tricky.
Absorbing energy leaving the outside.
Good. So this is my system. And obviously everything else is the surroundings.
It's just like an ice cube sort of ball.
Good. If we are absorbing energy, again, we're taking the system's point of view. So energy is coming in. The energy for the system is going to be positive because it's gaining energy. But if it's gaining energy, that means that heat is being transferred from the surroundings to the chemical reaction. If the surroundings lose heat, the temperature is going to go up or down in the surroundings. Again, it's losing heat from the surroundings, so what's going to happen? Temperature is going to go down. The surroundings are going to be cold. Okay? We'll do a chemical reaction like this in lab where the surroundings get really cold because the chemical reaction absorbs that energy. Okay, it looks like we got it right. Let's go to practice problem number 3 now. Will the energy sign be positive or negative for a chemical reaction that releases energy to the surroundings?
Negative.
Also, will the surrounding temperature go up or down?
Up.
Okay, so let's go to the sign. What's the for the reaction, for the system? It's releasing energy, so heat is going this way. So the sign for energy in the system is going to be what? Negative. But the surroundings, is the temperature going to go up or down? It's going to go up. Yep, because it's getting more heat. It's a new pen, it makes a squeaky sound. Okay. Heat can be absorbed or released in a chemical reaction. We know that. Heat can either be released or absorbed in a chemical reaction. Well, here's where it gets a little more complicated. It's not good enough for chemists to say it's going to gain heat or it's going to lose heat. We want to quantify it. So when chemists quantify that, they call the change in heat energy enthalpy. And it's given the symbol capital H. But they're not concerned in really what H is. What they're concerned about is the change in heat energy or the change in enthalpy. So on your notes, I want you to write this, okay? When you see a delta sign in science, what does that mean? It means change. What does change really mean? How do you calculate change? Well, you take final minus, you take the final minus the initial. So when we talk about delta H, what that equals is H final minus H initial. Okay, please write that in your guided notes somewhere. We're going to be using that equation all chapter. All right, enthalpy. Well, we talked about it. It's a measure of heat energy. You're supposed to write down the definition. Okay, so let me give you a second. Write that in your notes. So enthalpy is the amount of heat energy released or absorbed during a chemical reaction. What's the symbol for enthalpy, guys?
H.
Capital H. Capital H.
We did this last year in chemistry.
We did. We introduced this a little bit last year in chemistry, yeah. Yep. Okay, so chemical reaction can have the following energy changes. This is where you're going to identify what we talked about last year in chemistry. We learned about exothermic reactions, right? What does exo mean? I want you to make this note. What does exo mean? Exit. What does thermic mean? It means heat. So heat is exiting in an exothermic reaction. So let's talk about that. Energy is released. If energy is released from the reaction, the surroundings are going to get warmer. And delta H is going to be what? Negative. The sign is going to be negative because you always take the system's point of view, which is the reaction. It's losing heat, so it's going to be negative. Okay, number 2. Chemical reactions can be endothermic. What does endo mean? Yeah, it means enter. And what is thermic again? Heat. And so this is where energy is absorbed. And the surroundings become colder because the reaction is absorbing that energy. That means the surroundings get colder. Delta H is a positive number. Because now the system or the reaction is gaining that energy, so it's going to be positive. Okay, very good. Let's go through an energy diagram. We talked about this last year in chemistry, but now let's build upon that knowledge, okay? This is an energy diagram for an exothermic reaction. Okay, energy is measured on the y-axis. We measure that energy in terms of enthalpy, so I'm going to put capital H. The amount of energy that the reactants have is plotted right here. Let's just give it a number. Let's say it's 100. 100 what though? What do we measure energy in terms of? Joules. So let's put a capital J for joules. That has 100 joules. Well, for the reactants to react, you've got to reach the top of this hill. What is this hill called again? You guys remember? That's activation energy, the amount of energy needed to start a chemical reaction. Now, once you reach that peak, the reaction is going to go to completion and you're going to form the products down here. But notice, do the products have more or less heat energy? They have less. Let's give it a number. Say it's 50 joules. Guys, what is delta H going to equal in this reaction? It's going to be negative. How do you know that? What was the final? Because we do final minus initial. What was final? 50 joules. What was initial? 100 joules. What does that equal? A negative 50 joules. Okay? Now, let me emphasize this point. Ethan, the energy here, was it just destroyed? Where did it go? We had 100, now we have 50. Where did it go?
Into the shrimp.
Very good, Ethan. I mean, hey. Okay.
That was all me.
It's leaving in the form of heat. You can't destroy energy. So what goes to a higher temperature then? The surroundings. They're gaining that heat and they're going to get hot or warm. Okay, endothermic. Let's draw an energy diagram for an endothermic reaction. Again, we have energy, so it's H here. Let's say that now we're starting at 50 joules. The reactants are starting at 50, and it goes over the activation energy, and we end up over here. Let's just call that 100 joules. So now what's delta H, guys? Positive what? Delta H final was 100 minus the initial of 50. What does it equal? 50, and what do we measure energy in terms of? What units? joules. Okay, again, let me just emphasize this. We started with 50. We ended with 100. Can we just create that much energy here? No, where did it come from? Where did it come from? Heat was absorbed from the surroundings. So now are the surroundings going to be warm or cold? They're going to be cold. Okay, so hopefully that makes sense. Okay, endo or exothermic here, guys. Pop quiz. The reactants were up here, the products down here. Delta H is negative. Exothermic. Heat is leaving or exiting the chemical reaction. So this one is exothermic. Okay, could you guys answer this question? Endo or exothermic? Obviously it's endo, but how do you know it's endothermic?
Because it says it at the bottom.
How else would you know that? Because we have a delta H that's positive, that means heat is coming in, heat is entering, right? Okay, practice problem number 4. Draw an energy diagram, guys, for this reaction. But before you start, heat is on the right side. So is heat entering or is heat exiting? Exiting. So draw an energy diagram for this reaction. Okay, so hopefully when you draw an energy diagram, we've got on the y-axis energy. What do we measure energy in terms of in chemistry? Enthalpy, which is given a capital H, but yeah, in terms of units, it's joules. And then reaction time is on the x-axis, down at the bottom here. Okay? Well, if heat is being given off, we know that this is an exothermic reaction, okay? Because heat is being released, so that means exo. Well, if heat is being released, that means we're starting up here somewhere. This is CH4 plus 2O2. Those are our reactants. Now it's going to have some activation energy, and then it's going to come down here, and this is what CO2 is going to be found, and our water. Okay? Let's say that was 100 joules. This was 50 joules. What's my delta H, guys? The difference from the reactants to the products. Delta H is in minus 50 joules. Okay. Well, I just made up these numbers. I just made it up. I'm just showing you that it's going to be negative. I just made it up. What you were supposed to do is just draw some shape like this. How many of you guys got that? Okay. Can we just destroy this much energy? No, it's leaving in the form of what? Heat. So the surroundings. If you touch that beaker, it's going to be what? It's going to be hot. It's going to be hot. Okay, so hopefully it'll look like that. Number 5, I think we can get through this one, guys. I want you to draw an energy diagram for this reaction. Guys, if heat is on the left, now is heat entering or is it exiting? It's entering. That means endothermic. So let's quickly draw that. Okay? So this is our enthalpy. We're starting low. We go up over the activation energy hill and we end here. So this is our reactants. This is our products. The difference, delta H is going to be what? Positive. Can we just create that much energy? Where did it come from?
The surroundings.
The surroundings gave us that heat energy in order to do that. So if you touch that beaker, is it going to be hot or cold?
It's going to be cold.
It's going to be cold. Okay, I would like to finish with one more slide here. This is a good one to end on. What it is, it's water phase changes. So we've got a piece of ice down here. Stay with me, guys. Okay, so there's my ice. We've got a puddle of water. And over here we've got steam. Guys, to go from, let's do number 1. Is it endothermic or exothermic if we go from a solid to a liquid? If we have a piece of ice, does it have to gain heat or release heat?
It has to gain heat.
Has to gain heat. So this is an endothermic process. Okay, let's do number 2. Let's do number 2. Brett, help me out. If you're going from liquid water here to gas, does it have to release heat or does it have to absorb heat? Absorb heat, so that is endothermic. Okay, number 3. If you're going from a gas to a liquid, so now we're at a gas, how do you go to a liquid? It's got to do what?
Loses heat.
Lose, which means what?
Exothermic.
Exothermic. Now let's go from a liquid to a solid. It's got to do what in terms of heat?
Also lose heat.
It's got to lose heat. That means exothermic. Okay, so hopefully that makes sense. Endo and exothermic processes. Just remember what an ice cube would have to absorb heat to become water. So that's absorb heat is endo. So everything that goes this way is endothermic, and everything that goes this way has to release, so it's got to be exothermic. Okay, guys, I think we'll stop there. Before I end the video, though, you've learned enough to do the endo and exothermic reactions worksheet in your student workbook. So please go to your student workbook. Again, it's called Endo and Exothermic Reactions Worksheet. Please get that done. And hopefully we learned something. Hopefully this helped.